is a familiar setup, a diagram showing a pair of magnets with the opposite poles facing each other. N pole of one magnet is here and the S pole of the other here. Between the two different types of poles, we have a loop of wire or a single coil, this, with ends connected to a part called the split ring commutator. Each part of the ring touching brushes, which is connected to the two terminals of a power source, the part of the circuit that provides the EMF or electromotive force, so we can have current in the loop. Now, because of the orientation of the terminals, we know that the current, to be consistent with the previous concepts I discussed, our current is the conventional current, which is from the positive terminal. So in this part of the loop, the positive charges move in this direction. Note guys that inside the wire, the particles that are actually moving to produce current are the electrons. But since we are using the conventional current, which is the opposite of the real electron flow, we can say that positive charges are flowing and the direction of their motion is pointed this way. Now, the pole at the left is an N pole, and so the magnetic field is going this way, directed from N to the S pole. The direction can be drawn using an arrow like that, this blue arrow here, representing direction of the magnetic field. With these kind of orientations, we can easily see that this part of the loop is experiencing a force that is directed downward, like that, represented by this green arrow here. The current flows around the loop, and that at this portion of the loop, the conventional current, let me highlight this, the conventional current should be directed this way, and that the field is also in this direction. These two directions tell us that the force experienced by the wire here should be in this direction, upward, opposite to the force acting on the other part of the wire. We have a downward force here and an upward force here, and that if we assume that this single coil of wire is free to rotate here along this line, we can easily see a turning effect. Remember the moment of force. There is a clockwise moment due to these two forces, making the whole loop turns like that. Let's have a very quick recall of the idea how we determine the direction of force. The hand rule, remember? Okay, uh, like that. All right. Okay, now we have left hand with this second finger pointing to the direction of the magnetic field. This third finger positioned like that, roughly perpendicular to the second finger, which is representing the direction of the current. Current is a scalar quantity, supposedly having no direction, isn't it? But usually, people would say direction of current. When they do, they actually mean the direction of motion of the charge that produces the current. In our case here, the third finger points that direction. Now for the thumb, this points the direction of the force. This idea was first introduced by Fleming, so we are calling it Fleming's left hand rule. Interestingly, also, guys, that in some parts of the world, people are calling this father, mother, and child rule. Basically, because of the quantities involved. Father here, mother am, and the C child here. You can use that if it can make you remember the directions easier. So this movement of the loop of wire in this condition here is what we call motor effect. Motor is a device that converts electrical energy, the electricity here at the source, to a mechanical energy or work, which is in the motion of the coil. Here, it moves in the anti-clockwise direction. Now, an interesting idea is that if we can do the opposite, can we do the energy transformation from mechanical energy to electrical energy? All right, we'll see about that. But for a starter, you are all aware that there's this device called generator, aren't you? Okay, anyway, we will go back to that later. Let's now just proceed to the idea. Let's erase these. We do not have current at the moment and the force too, so we are erasing this. Okay, we do not have those yet. Okay, so we want to do mechanical work or use mechanical energy. We can do that here with the same loop. Imagine we are manually making it rotate anti-clockwise like that. Let's analyze what is going to happen to this part of the loop. Let us make it bigger and bring it here, this one. Black line represents that part of the loop that we want to analyze. And this wire is in the region where there is a magnetic field. Here, from N to the S pole of the magnets, let's draw some arrows, blue arrows to represent magnetic field lines here, from left to the right, following the idea that it goes from N to S poles of magnets. There are field lines above and below the wire, so maybe it would look better if we erase these parts here like that, so it appears that field lines are there where they should be. Now, when we rotate the coil manually, this wire obviously goes down, and that we can think of all the particles inside, like protons, neutrons, and electrons, are also moving down, like the way we see the wire moving down. It is just like when you are inside your car's motion is roughly the same as your motion. All particles here move downward like that. Since they move in a region where there is a magnetic field, then we may be able to apply the hand rule again. This red arrow here represents the direction of the motion of the charges, which we can assume to be positive. Again, that's for consistency with the type of current we have been using from the very beginning, conventional current. If we point our third finger downward and the second finger to the direction of the magnetic field, which is to the right, these arrows, then these charges will be acted on by force, which direction we determine using our thumb. This charged particle will be pushed this way, this one, this same direction, and the other one too. And all these particles in this part of the wire will be pushed like that. It's not so clear, so let's use a different color. Maybe white is good enough. All right, here. This is the direction of the force or forces acting on the charged particles. Because of that, there will be a conventional current to be induced in this part of the wire, directed this way. All right, let's note this down and put it in the loop. Let's erase this first and these ones too. Okay, this arrow, red, is representing the conventional current here. Now, how about the other side, this wire here? We use again the hand rule, but this time, because of the kind of rotation we have, it looks like the motion of this other part of the loop is upward. Alright, let's just erase this and draw an upward arrow. Alright, like that. To represent the direction of the charge as a consequence of the movement of the wire. The hand rule will tell us that the charges are going to be moved by the force in this direction. And so we have a conventional current at this part of the loop, with the charges producing that moving in this direction. All right? The overall picture, guys, is that we have a flow of charges from here going around like that to here. A current is induced. Remember the definition of current. Current I is equal to the amount of charge that passes a point at a given time. When we started with this, there was no current, but because of the movement of the wire in the region where there is a magnetic field, we get the current. That happens because work is done per unit charge to move these charges around the loop. Familiar? That's the electromotive force, yes. It is like having a battery around here. Reason why we have current. The symbol, lowercase epsilon, electromotive force is generated. Devices that do this are called generators. Mechanical energy from the motion of the coil being converted to electrical energy here. If we connect electrical appliances here, and if the needed voltage is correct, those appliances will work. So what you learned just now, guys, is the phenomenon called electromagnetic induction. And this electromagnetic induction is summarized usually through two physics laws. Let's color this so I can do quick explanation about those laws. Okay, there we go. Now, the flux. Alright, this is not the law, but one law is dependent on this, so we need to know what this is. Don't worry, this is just a human construct that means the number of field lines that passes through a given area. The law is saying that in order to generate the EMF, the flux must be changed. So when we rotate this, say it becomes like this, tilted a bit, through the area, the loop doesn't change, but the magnetic field lines that pass through the inside will change. Then we have a change of flux. This law was first taught by Michael Faraday So they name it Faraday's law, which states that the induced EMF is directly proportional to the rate of change in the flux. Faster rate, more EMF. Now, the second law is called Lenz's law. Take a look at these terminals here. Originally, this was noted negative here and positive here. However, our induced conventional current flows this way, which tells us that the induced electromagnetic force has a direction opposite the motion producing it. It must be like that as determined through the hand rules earlier, and that if otherwise, conservation of energy would be violated. Interesting, isn't it? Just don't have much time. I'll go through the details next time, okay? I have to make sure my videos are less than 10 minutes, so that's all for now. We will take a look at some other physics stuff in your syllabus related to the electromagnetic induction some other time. Bye.